Our distinguished speaker of the evening has more than 25 years of tech leadership, has formerly spent 10 years as the key engineer for Sybase, and was formerly the director of SQL Server. Please welcome the VP of Engineering of Clustrix, Robbie Mihalyi.
Thank you for having me, and I apologize for conflicting with the host visit next time. And so we're going to talk about today about the architecture, scaling strategies on the web. But if you signed up for this, which I will change a little bit, we're also going to talk about the same thing. So we get two presentations. And so what I want to cover today is capacity, elasticity, and resiliency, and not only on the database, but also in the application. So one of the things on Sybase, what I've done is went to companies that build applications. So most recently, I was at Marketo. Anyone know about Marketo? Yeah, I know about it. And so some of the scaling strategies that company use we'll talk about it a little bit. Now, all of this is in the context of the cloud. And as I was thinking about this, what it occurred to me is that the cloud really democratized and commoditized the hardware resources. If you think about this, 10, 15 years ago, you had to buy a lot of hardware, set up networking, hire people to be able to set up an application environment and publish. And so what the cloud brought forth is the ability to just go to a place and spin up any number of resources. And according to what you have, you pay even by the hour or by the day, by the week. And what's also very important is that you make your application accessible to the network by public. And if you need more capacity, then you can just add more machines. And as long as the software can deal with it, you can get more capacity within your system. Now, there are a couple of, obviously there are a lot of providers, but I put some of the top ones up there, Amazon and Rackspace. Those are the platform as a service companies, but also you have a lot of SaaS applications where you can actually do development online, such as Heroku, and even Salesforce. In Salesforce, you can do applications and implement application logic specific to your needs inside Salesforce. So it's really cool. So the cloud really brought a lot of accessibility to set up systems. Now, probably you might have run into this, is that if you share resources and everything is virtualized, then the performance characteristics of your application will vary. And some applications don't necessarily care about it, but others, if you have very specific performance needs, then a shared environment might not necessarily work. So then you can go to even dedicated virtual or even hardware resources in some providers. There you lose a little bit of flexibility, you probably pay a little bit more, but it's still an available environment for your application. Now, you probably have seen in the tagline, Clustrix is really focusing on e-commerce, and I felt that e-commerce is really a great match for the cloud. How many of you do e-commerce? Okay, so hopefully this will resonate what I'm talking about. One of the companies I worked for also provided a e-commerce platform and also e-commerce service. And some of the capacity needs were pretty amazing. That at certain times of the year or certain events created this huge demand for capacity. We had companies that made 70 to 80% of their yearly revenue just a handful of days a year. So you can imagine the pressure on the resources, on the staff to make sure that the capacity is there. And the throughput. The throughput is very important because you suddenly have higher conversion rates, higher transaction rates, so those needed to go through the system so you don't lose sales. At the same time, latency is also an important factor. Because latency eventually translates into response time. So if your transactions start taking longer and longer, eventually users on the other end will start seeing that the site is sluggish and slow. And depending on what research you look at, anywhere from 4 seconds to 6 seconds, you start losing customers really quickly. So if your web page doesn't load in less than 3 seconds, basically, you're most likely to lose a customer. And around 6 to 8 seconds, you guarantee to lose a customer because they don't have patience. And then, when you have all this activity going on, the highest throughput, highest transaction, lots of users, uptime is the most important. Because the moment you go down, you start losing money by the minutes. Again, one of our customers figured they were losing anywhere from $50,000 to $100,000 a minute once they're down, because they had high value transactions going on. So anyway, so this is a little bit of a side note here about the cloud and commerce, and I'm going to come back to this throughout the presentation. So let's talk about capacity. So when I think about capacity, I think about scale, first of all. Can I take more data, more users, more sessions? And it translates into throughput. So can I process more transactions? Can I take on more concurrency? And then is my response time staying constant throughout the increased capacity? And that's a challenge. Now, if I separate application and database for a second, and I'm just looking at the application stack. So if you have a PHP, a Ruby on Rails, or Python, or any other application framework, it's pretty easy to scale. Because usually they're independent systems. They put data in the database, but for now we're not going to talk about that. We're just going to look at the application, and you can scale that pretty well, pretty easily. If you have a load balancer, you register your application system with a load balancer, and you keep adding systems to it, and you have increased capacity. If you're really fancy, you can add a redundant backend network and separate the incoming traffic that's coming from the web to separate it from the database traffic that goes to the back. And it's a very typical sort of 2-tier, 3-tier setup. Scaling databases is very hard. And what is interesting is that when I worked at Sybase many years ago, this was the same issue, right? How do you scale? How do you get more out of your database? And so, obviously today is also an issue, but it's becoming a problem because now you have to think about what I'm going to scale. Am I going to scale reads? Am I going to scale writes? Am I going to scale both? Do I have to trade off one versus another? So that's a question and an issue that has to be addressed. The second is data consistency. Now, there are all sorts of discussions about the various consistency models, but to me, I'm used to that when I write something out into a database or a file or something, I'm expecting to read back that data. Regardless whether it's distributed, whether it ends up somewhere else, I'm expecting that data or the data set to come back to me. And so data consistency is very important. And if someone updates that data, then I see the update report. Now, in the relational model, we use the ACID properties, if you care about those. And the ACID properties assure you that all the elements within a transaction either commit or roll back, the atomicity of the transaction. The consistency again, isolation, so you don't see, so the locking mechanism ensures that you don't see half changing data, and durability. So if anything goes bad, anything goes down, the transaction is not lost. If again, in the e-commerce world, if you already put the order in, you charge the credit card, and right after that the database crashes, you cannot say, oh, well, we just lost that transaction. And even though we charged you already for the item, you don't know what to ship. That would not be good. And then last but not least, again, is the throughput and latency. So when we look at database scaling, these are some of the issues, and there are obviously others. So because of this, and because of relational is hard to scale, a while back, a lot of non-relational NoSQL databases came into bear. And the thought was that not every application needs a truly full relational ACID database. And it's very true. If you want to insert a lot of data, so for example, if you have clickstreams or app tag or IoT, Internet of Things, and just want to collect a lot of data, you could collect those in key value pair. Forget the ACID properties, you can just plot data at the speed of light. And so the physics, right, if you eliminate all the overhead, no referential integrity checks, no locking, none of that, you can easily scale and put data really quickly into a database. Now, the problem is that once you have the data, you have to do something with it. And so doing something with it is you have to read it. If someone asks for a report, suddenly that data is not structured necessarily well enough to do the report. And so you have a challenge with that. My inclination is that relational databases will provide these kind of capabilities because it's much easier to go from a relational model and relax the ACID properties and provide the key value pair store in the document store with a different, more efficient store that's relational. And it's easier to do that than a non-relational database to go fully relational. So here are a couple of examples. Value pair type databases. Memcache and Redis, I usually have seen that used as a cache with the application. It's really not necessarily a database, but it's sort of a database that allows you to store objects and just random data into a cache and retrieve it really quickly without having to go through the network and a database. And of course, there are other type of tabular or columnar data stores, and as well as document. There's also spatial data stores. So there are a lot of different specialized data management systems that store data very efficiently for a very specific purpose. So what about relational database? Well, I'm going to use MySQL as an example because, again, we're a MySQL compatible database, and well, pretty much everyone has used MySQL at one point or another. So I'm going to use that as an example. And so with MySQL, you have a number of different choices to scale and gain capacity. One is to scale up. Right? So you buy a bigger machine, more cores, and bingo, your system runs really fast. The problem with that is that at some point you run out of steam on that machine too. And as you want more and more performance, you get to more and more cores, faster and faster machines. At some point you either hit a wall or you pay a lot of money to get some exotic hardware in place. But it's very doable if you know that you have a certain limit to your capacity that you need. That's a viable solution. Another option is to say, well, maybe I just need reads to scale. Writes are okay, and I want to scale the reads. Well, the replication allows you to do that. Pretty much all databases support replications. So you can replicate out your transactions from a master to slave, and then you can either modify your application to read from the slave, or you go to a proxy that knows that these type of queries will go to a different server, and the write transaction, the modified data will go to the master. Again, as only read performance, data consistency could become an issue. So it depends on the latency or the delay in the replication and the recovery of that, or the read of the replication on the slave side. You might read data out of sync. So the application has to ensure that there is some sort of synchronization if it really cares about specific data elements. Well, what about writes? So you can set up MySQL in a master-master configuration where basically you can write to multiple systems simultaneously. It can be used very efficiently, but you have to be careful that if you modify the same records, the same primary keys, now you're going to have data conflict. And conflict resolution is not trivial by any means. And so your application has to manage that somehow. And actually, there are middleware applications that allows you to do some of that, but ultimately your application has to reconcile inconsistencies and conflicts between two data, same data, not data in two different places. What about scaling reads and writes? Well, sharding is one of those things that can become popular to say, let's distribute data across multiple clusters or multiple nodes, and pick a key or a collection of keys and shard the data across multiple nodes. And so that adds you both read and write scaling. Now, here again, the con on that one is that it's going to be really hard to do referential integrity because you have to take all of the foreign key tables with the data and appropriately distribute that. Doing consistent backup across all of these would be very hard, so you have to do individual systems by themselves, and you could still end up with an unbalanced read and write scale, right? If all of your, if this were a phone book, probably most of the people will be in the S category there that you would query and update, and so a lot of the queries would be, we call it lumpy. So it's not nicely distributed. We have this big bump where one machine is pretty heavily loaded, even though they're distributed. I also want to mention MySQL cluster that was primarily designed for telco and with the emphasis on high availability, but it does provide you with a multi-master replication model and provides high availability. Now, we have heard that people, like for example, the global checkpoint takes over 2 seconds, so your consistency across the cluster can lag. And so if you have a lot of transactions going on, that eventually adds up, and so you can be behind in this whole consistency model on your database. It only supports statement-based replication, and then range scans, so if you have to go across all of the nodes to do a range scan, that can be really slow because it has to shuttle data across the network to one of the nodes that returns the data, the results. And it's unclear, how far it scales. Probably 3-4 nodes, maybe 5 nodes even works, but beyond that, nodes, we haven't seen deployments of large scale deployment SQL cluster. And as I mentioned before, a lot of companies, Salesforce, Marketo, a lot of companies, application companies, use what's called a workload partition. And this is typical for a multi-tenant environment where you have different customers, and you basically profile the load for each customer, and based on that, you assign it to a pod. A pod is a combination of application, server, and database. And it's pretty straightforward. You can have multiple applications, but the database typically is one database, maybe replicated so it has redundancy. And you have multiple pods, and that's how you scale. Now, you can scale that infinitely, right? Because the pods have nothing to do with one another until someone asks for a report across all the pods. And if management asks for that, then I'm sure the sysadmin and the guys who are in charge of the applications query around and figure out how on earth are we going to run a report across all of these databases and provide one view of what's going on. So it's a complex environment to set up. If you have schema changes, you have to do it on every database. And again, it's a complex environment to support. So that's about capacity. It's quickly, I'm running through this. So let's talk about elasticity. Now, the way I think about elasticity is that how easy is for me to add or remove capacity. Yes, sir.
So on the capacity side, so this is a solution.
No, there is a solution. Absolutely. So the question is that the gentleman says that there's no solution for capacity. Absolutely, there is. It's just they're hard to do, and you have to understand what to trade off with one solution versus another solution. That's all I'm saying. so their solution, software will say it's possible, but just given resources, time, and what it takes to do. And sort of this elasticity goes into that part, that how easy it is to scale up and scale down. And in this case, we termed this elasticity is flexing up or flexing down. How easy is for me to add any resource? Will the system take advantage of that? And when I don't need it, so when we talked about the e-commerce companies, when they have to provide for 10x the normal scale, well, they don't want to keep paying for that all day long, right? Because they use it maybe on a handful of days or maybe 2 handfuls of days, but you don't want to keep paying for that. So you need to be able to gracefully shut them down and then bring them back again when you need them. And you only pay for what you use. So if I take a quick look through all of these systems, application, again, is easy to flex up, easy to flex down. You bring up an application server, again, you register it with your load balancer. Application server can go down, whether you register it or just dies the HA. For example, in HA proxy, you know that system is non-responsive. So it's pretty easy. NoSQL databases are also, again, are designed to scale. So it's relatively easy to add nodes and scale data to many, many terabytes and terabytes. Unclear if you can flex down. So not sure if there is methodology to, for example, take some of the data partitions that have been put onto different nodes and reconcile them with the existing nodes, so flex down. Although they do have high availability capability in some of these non-relational databases. Scale up, well, it's expensive to flex up because you have to basically take your entire application, put it on a new machine. That's very expensive, and once you're there, you don't want to flex down. So that's pretty much not applicable. The master slave is reasonably simple to set up. Those who have done it, it's not a big deal. And then you can basically turn off read slaves. Now, as long as your application doesn't go and reads from or goes and tries to read from that slave, you're in good shape. Master is somewhat more involved, again, because you have a conflict resolution, and so your application is already modified for that purpose. So scaling it down or flexing it down might be more involved. Sharding is expensive, and once you sharded your database, to reshard it again to fewer nodes, it just is not feasible. Just a lot of work, and so you don't do it. And in terms of MySQL cluster, again, it's very similar to the master, and the application partitioning is also complex. And so sometimes I've seen where people try to consolidate like 2 pods into one because you have faster machines. It takes a lot of work to do that. And so again, it's not entirely feasible to do that. So now I'm going to go quickly to the resilience piece, which is really fault tolerance. So how well your application environment survives a software or hardware failure or network failure, things like that. And so here again, to the application, no single point failure, one of the servers can disappear. Maybe some transactions might have expired on that, but the rest of the system will continue to work. And it's pretty easy to scale them up and down. For NoSQL databases, again, some provide that high availability, and so there are copies and replicates of the individual partition on other nodes, and they can cut over. On scale up, you have a single point failure. If that machine goes down, you're pretty much stuck. So now you have to create the replicates and copies of that system to be able to cut over in case the master fails. For the master slave, we have the failover, the slave, and master, again, it's resilient to any of the masters failing. If you're multi-master, until you have one working, you're still in good shape. Now again, you can still have data skew issues or data consistency issues that some of the replication components have not played back. Sharding, you have multiple points of failures. Unless you replicate each of the nodes, each of the machines with their own horizontal partitions, you would have multiple points of failure. MySQL cluster is the same way, and application partition is the same way. So to just summarize the whole thing, if I'm looking at just relational databases only, yes, you can scale up. So the answer is you can scale up, whether it's expensive, whether it's flexible, but you can do it. I think with elasticity, I have to conclude that we really don't have elasticity at the level where an application can. In other words, bring up a node, and suddenly, by virtue of bringing up that one new machine, now you have extra capacity. There's always some work involved in scaling up the database. In this case, MySQL. And then, in terms of high availability, yes, there is support, and it can be a failover. But in a master-slave case, you have to make sure that your application, the entire application, can talk to a different server in case the primary server goes down. So again, it's still involved, but it gives you an opportunity to do failover with MySQL. So at this point, I'm going to talk about Clustrix. How many of you heard of Clustrix before you registered for this? Okay, so a few, so that's good. I hope I can add more information from what you know. And so what Clustrix RDBMS is a full ASIC compliant relational database that is designed to deal with this, to these very issues. Scale, so managing capacity, managing flex up and down, and have failover built into the very architecture. And it's MySQL. So let's see how this works. The architecture is a shared nothing symmetric architecture. The reason why I underline symmetric is that every node is equal, is the same. There's no master node, no aggregator node, no specialized node. All nodes in the cluster are equal. So that allows us to scale the environment. And so each of the nodes contains a query compiler that is capable of requesting, of receiving requests and parsing it, compiling it, and executing those requests. Each of the nodes contains the data map of the entire cluster. So that means that a node can make a decision without having to query all the other nodes of what to do with a SQL request. The database engine can perform any and all of the functions that if one, it doesn't matter which node you're talking to, they each can do exactly all of the functions that any other node can do. And then finally, we slice up, we do a data distribution based on independent key, and we slice up tables into individual slices, which I'm going to go into more detail. And so when you create a table, when you alter a table, we auto-split data into slices. And the way this works is that we partition the table vertically and horizontally. And the horizontal partitioning is the slice mechanism, and we distribute those across all the available nodes. In addition to that, we create replicas or copies of each of the slices. And if you notice, that each of the slices is a copy of each of the slices is on another node. So basically, there's no single point failure in this picture, because if one of the nodes goes down, then the other two nodes in this case will have a copy of any of those slices that was lost basically because of the failure. Now, this allows us to flex up very easily. So you add a new node into the system, and we have this magic system called the rebalancer that automatically goes in and redistributes these slices to all available nodes. And so this allows us to handle reads and writes very easily and scale. And the high availability is built into the system, right? So it's architected based on our partitioning scheme and our rebalancer scheme. The application always sees a single instance of the data. So it has no idea where the data is coming from, but it always sees, like when I look for a table, I go those come out, I always see that very consistently. And so the application doesn't have to know anything more than what is the SQL interfaces to the database. If one of the server goes down, then the process is reversed. The nodes that node that contain those slices will be actually recreated on the remaining nodes, and it's rebalanced. And this process can go back and forth. Yes.
What do you do how do you handle duplicate records?
How I can,
So when you add a new node, there's going to be duplicates while the data is being copied, I'm assuming? Because it's being copied.
how we handle duplicate records, I'm not sure. So if you're saying if there are transactions in flight.
So if you add a node here,
Mhm.
you're going to move data from 2 of the other nodes, right, to balance?
Right.
During that balance, there's going to be 2 copies of the record, right? It's
Right.
got to be copied over and then deleted.
Right.
Right. Well, during that, how do you account for
So
that?
we queue, so if there are changes to those records,
Mhm.
then we queue it up to that record to replay, or to those slices to be replayed once the slice is active. So there's a whole process that the rebalancer goes through where it marks it starts to create a slice, so it creates a container for it, and it starts marking the slice that it moves away as invalid, so transactions do not go to those slices. Because if you do updates, right, you have to put those updates somewhere.
Right.
So the question is where you put it. And so that's why you have a queue mechanism that the moment the second slice is up and alive, the first one that was copied or moved is not accepting any more updates.
Right. But during that move, you technically have 3 copies, right? You have the master, I guess,
Right.
the slave, and then the one copying?
But they're marked accordingly so you don't create duplicate records. So you have always the same
So
record number
the
of
counts are
records
consistent?
active.
Like if you did a sum of a count of the records, it wouldn't pick up a duplicate count?
No, it wouldn't.
Okay.
Yeah. Yes.
So to do that, you use like
count the slave.
like
Mongo does that problem.
No, it's not.
If you
It's a
count the
built-in.
slave, it's
So
always-
we have internally we use a Paxos algorithm for do.
But you gotta read it. If you read the slave, which slave does it read?
And so we manage this whole synchronization across the nodes to again
Right.
not to create duplicates.
So you have 2 slaves and 1 master.
Or not.
If you read from the
few
slave.
transactions against a slide that's.
I'd have to see if it works.
so a node, just one little follow-up, a node needs to know at least one other node and knowing
So each node knows about all the nodes. So there's a map of because when it comes up, the rebalancer updates the map. Actually, I'm going to go through a little bit on how that works. Pardon me? No, there's no replication involved. We all move the data under the covers.
You said there are 2 copies of the whole piece of data.
Right.
On your system, so that means simulation.
Well, you can have more than 2. So you can specify how many copies, how many replicas do I want for this table. And so all slices will be duplicated multiple times. And again, this is a reason to have failover capable for high availability. So any single node cannot invalidate
You
your.
don't actually need to delete anything, you just can mark them as, active.
Exactly. Yes.
But you need to run something. Now, how your cluster knows that some copy is done?
Some system is down, so we have a heartbeat mechanism that goes around and checks every once in a while, and I forgot what I think every 10 seconds or so, whether a node is alive. And again, we have every node contains a map of all the other nodes and knows who's alive and who's available, and it updates that as soon as one of the nodes is not responding, then there's a reprime mechanism just in case the node is stuck. And at some point, that node is going to be marked as not responsive, and this whole process starts.
The cluster needs to somehow
Yeah.
synchronize itself in order to know
It comes back up like the processing.
Right, and that's the job of the
copies that are
rebalancer.
mismatching and all the nodes should be more valid.
The rebalancer is that process that does that does the rebalancing. Yeah, it's ours. Yeah.
It comes back up, it doesn't stop. So then you have 3 copies.
what's your,
But that was a different.
There's no maximum. We tested, we have customers that have, 30 nodes in production. So it's high, and we tested even beyond that. So we have not seen, it's going to be limited by network bandwidth at some point. So even though you share nothing, you have to share something, and as the network. And so we're low footprint on the network, but at some point you can saturate that. And so you can have redundant networks, multi-network cards, and so increase your network bandwidth with that. So the system also does distributed query processing. So any of the nodes, again, since it's a symmetric system, any of the nodes can take an incoming request and process them. And furthermore, every node can then dispatch parallel work to all the other nodes and take process and close to the data as opposed to moving data around. So I have a little example of that. We also support replications, a MySQL compatible replication, statement-based and row-based, and our backup is parallel and fast. So let's look under the hood and talk about these details that we're trying to get to. So the key components to enable scale-out, as I mentioned already, is the shared nothing architecture. And so we don't share disk, we don't share cache, we don't share anything else other than the network. And so that allows us to not have any critical bottlenecks that cannot be extended. So the rebalancer is this system that runs regularly and looks at the state of the cluster and establishes whether it needs to copy or move slices from one node to another, or it needs to create any copies. So again, we're going to have some examples of that. And it needs to create a new copy because, let's say, one of the slices is underproductive. Query Optimizer with the evaluation model basically can take queries and split it up into multiple components, we call them fragments, and send those fragments close to the data. So if you have a distributed join, a distributed aggregate, those all can be processed together. And this evaluation model looks at what's the best way, where's the relevant data where we have to send individual fragments for, let's say, a partial result, which then, of course, will have to be sent back to the requesting node to assemble that. We use multi-version concurrency control and two-phase locking to basically serialize the writers to the same role, basically the same record. So that's a regular row-level locking. But the MVCC will not lock readers from handling the writers. So the MVCC take a snapshot and allows readers to read that snapshot while someone else is modifying the table.
Is that table locking or row?
Yep.
Is that row level locking?
Yeah. Row-level locking.
Remember internal queues built?
It does introduce some, but we use a legal log, basically. So we use a log already that contains the previous version of the row to point any transactions that want to read and read from the log instead of reading the actual row that's being modified.
So you don't have to read lock?
Yeah, we do. Yeah, but it's a shared read log. So if you're already reading and you want to modify that, then obviously that will block. But if a read comes in after the transaction started, write transaction started, then the read will go to the to do the snapshot. And read from
So
there.
basically, a read for like the selector of it would be blocked, whereas a simple select.
Correct. Yeah. And our distribution mechanism uses an independent key mechanism. So we try to use the primary key, but if it's not selective enough, well, the primary key is going to be selective, but if we also consider other columns, and so we hash that into a 64-bit number space, and then those are divided into ranges, and then each slice owns a range of the data, and then the rebalancer distributes those slices across the various nodes. And so every table is vertically partitioned into representation. And representation is a collection of an index or indexes and columns. And so you have a vertical partitioning first, and then each of the representations are horizontally partitioning into slices. And again, the rebalancer then basically takes those and creates copies across the various nodes. You can have, typically, you have two copies. One is for the primary slice that you're going to read from, and a copy that you're going to maintain and update, so you have a protected slice. You can have multiple, so you can have even all nodes containing a copy of every slice. Now, obviously, that's going to take up a lot of room in terms of disk and cache and all that, so you probably don't want to do that. And the rebalancer ensures that there's a good distribution, and that all of those are balanced across all the nodes. And so this is the process it goes through. It queries the cluster. So there's a model, as I mentioned, across all of the nodes. But the rebalancer still queries all the nodes to make sure that any updates that happen that are for in transition are noticed. And it updates the model. And based on that, it decides, there are all sorts of complex rules that the rebalancer goes through and figures out, do they need to do something? And so those are going to turn into tasks. And those tasks are going to be queued. And then as they execute, the cluster is going to be updated, and then the models will be also updated as well. So this process goes on and on and on all the time. What are the tasks?
The multiple tasks there.
Yeah.
Is those tasks running on different nodes?
Yeah.
So tasks are running, there are no different tasks running the same node. They're always running different.
Yeah, on different nodes. Yeah. And so these are the various tasks that can happen. But there's a mechanism to ensure that no two tasks sort of collide with one another. So there's a certain priority, and then a certain intelligence between those to make sure that if I'm flexing up a node, I'm not flexing down the same node, for example.
So you're not flexing up the same time.
Right. Then if a slice is underprotected, meaning if I ask for 3 replicates and suddenly I have only 2, maybe because of a disk error or a node is flaky, then the rebalancer task will ensure that a new copy is going to be scheduled to be put on one of the nodes. And if the size is too big, we usually keep a slice about 1 gigabyte in size. By default, you can change that. But if it's too big, then you can split it up, or the rebalancer task will split it up and create multiple copies of the same slice. Yes?
So rebalancing takes into account frequency of access.
Frequency of access, meaning like queries?
Yeah.
Yes. Yeah. So it does.
It's like a hotspot would get more
Yeah.
statements.
Yeah.
You actually have much bigger variables than anything else, right?
Which one?
Rebalance.
Yes.
So basically, I mean, if something is wrong with your cluster, rebalancing is working like crazy, and the queries are stacked up and
Potentially, right. So if you have, for example, a lot of failures on your cluster,
Yeah.
then yes, the rebalancer starts queuing up a lot of tasks to start moving slices off.
Is it a problem that it may bring the system down, basically, it's like a lot of errors, right?
No, not really, because again, a lot of things are based on queues. So the system will try to work as much as possible. Now, again, if you lost 2 nodes, for example, that contain two slices, so one primary and one that was a copy, then now you have a problem. Then you have no
That's what the
recourse.
system does.
Yeah, but yeah, then at that point you have 2 points of failure, or sorry, two failure that happens simultaneously. Yes.
So I'm a little bit curious about key distribution. You're describing here how you flex up, flex down, basically the rough criteria by which you redistribute your keys. And now what I'm curious about is when you decide to redistribute a key, how do you decide which servers to move it to? And when you do, what is involved in the discovery of the location of an item? If I were to request a row by primary key, and I connect to any one of the nodes, how much work is involved in figuring out where that now resides?
Okay, well, so the server establishes based on, let's say, if it wants to balance based on access or size, right? So it discovers that the slice is too big. So in that case, it will split up that slice into 2 chunks in essence. Now they're not necessarily going to be equal size. So they could be one that's equal the size of the other.
So I've heard the actual discovery. So at some point I have to
Yeah.
have knowledge of where a particular key, let's say A, where I can find its replica.
Right.
So I'll have 2 or more copies. Where does that knowledge live? Is that knowledge held on every machine?
Yes. So every machine contains a data map of the replicate ranges. So you know about ranges, right? Because it's not any one key, but a range of keys for every node.
Okay, so you're implementing something like memcache's consistent hash algorithm.
Yeah, exactly. Okay, it's just a hashing algorithm, and so every node knows exactly what, when it looks at a data set, and it needs to establish where that replica lives, it uses that consistent hashing methodology to know which node contains that slice.
So that's, no sharing architecture
Yeah.
is about.
Yeah.
But it looks to me that this can be a much limiting approach, because once you scale to like 10 or 30 nodes, that probably is working. But if you will start scaling to like hundreds or even thousands nodes, like some of the systems are, I mean, there's no way you can hold the full map of everything which is happening in each and every machine.
Well, again,
You will run out of memory, no matter how much memory you have.
Yeah, so the map is based on consistent hashing. So it's, in essence, it's not having a copy of every data element in its system. It knows how to find every slice based on a predictive hashing methodology.
Yeah, but this is the same problem as saying no prediction.
Yeah.
You will not be able to scale beyond a certain number. I mean, obviously this number is greater than 30, but maybe 60 or 80, and you will not be able to scale up there until you will start splitting your full map of everything which is going into particular nodes, and then you are up to completely different tasks.
What we've seen so far is that as we scale up, we have not seen this kind of limitation, especially in an OLTP environment. Right? It's a workload dependent, and so will we run into 100 nodes limitation? Maybe. I mean, I'm sure we're going to test it, and so I don't know if there are these kind of limits what we're talking about. I mean, resources are, you can always have more memory, more disk, more of something to alleviate a single.
We're not going to
Yeah.
Well, not to the commodity style.
Yeah.
If you go to special hardware, then yes, but if you are addressing commodity hardware clusters, then
Yes. I mean, we primarily deal with, again, OLTP scale, not petabytes of data. We're not claiming that we're solving that problem per se. But we store a lot of, we have customers that have, what was it, 30 billion rows or something like that. They're processing very long. And actually, I have a couple of examples here. And so let me go through this quickly. The query optimizer is based on the Cascades framework. If you're familiar with that, Microsoft uses that, Tandem uses that, a couple of other databases use that. And it's really a Google-based, cost-driven optimizer model. And this is just a very simple snippet of what the optimizer needs to define or decide is, for example, what orders to join tables together. And so you probably know that if the join order is bad, your query just fails. If the large table is on the outer edge, then you scan the large table over and over again, so you destroy your cache and the query is slow. The other ones, which indexes to use, again, if you don't have the correct covering index, then your query instead of running in half a second will run 10 minutes. And in those kind of things. And then in a distributed environment, this system defines what can be run in parallel and what can have partial results that can be processed concurrently with all the others. And so here's an example where you get a very simple query, and so it happens that one of the slice elements is on a different node. And so we send the fragment, call them the fragment, it's a compiled down code snippet, so to speak, or function that is then sent to the other node in order to execute that function and return it to the requesting node. And we do the same thing, joins and aggregates, and stupid aggregates are definitely much more complicated, but work the same way. So the evaluation model and the planner figures out what can be done in parallel. Those happen. So if you do, for example, aggregates, it's really, that speeds up really well because instead of, let's say you have to analyze thousands and thousands of rows to get one value, each of the nodes can do that on their own and return those to the requesting nodes, and then the result returns to the application. The concurrency control, so again, readers can proceed pretty much using the MECC version, but writers do serialize on the same row through row level locking. Yes?
So you have to have a distributed commit protocol.
Yes. Yeah.
And what, any details on that? Or?
Again, as I mentioned, we use mostly Paxos as our group, general group commit protocol for getting quorum on the nodes, getting distributed locking and all that. So that's the mechanism that we use throughout the system. Two-phase lock. Two-phase lock. So basically, it's kind of like a two-phase commit.
There's some particular problems with the Paxos, right? There's a reason why some people kind of went away from that. With all this scalability. I'm not that familiar with it. I read that people was implemented that and then went away because they are at the end of the project.
Okay. I don't know any specifics around that. So a couple of examples. This is a workload with 9 nodes, 72 cores in AWS, and if I'm not mistaken, it's an IoT type application, which does a lot of inserts, updates, and a lot of reads. And on the average, the queries are around 5 to 8,000 per second, which is not big, but the CPU load is pretty low, so there's a lot of headroom for that. Another example is a app tech type application. Now, actually, the numbers here, you can double these numbers. Our news release is able to double this throughput rate, and so they process close to 100,000 QPS per second on an ongoing basis. And this has only 5 nodes, 100 cores, and they're planning to scale up from there. What's in development? So a couple of little snippets of what we're working on. Performance is always our first goal. And so we were able to read the lab 1 million reads per second. And we are also working on write scaling. I haven't talked about any numbers yet. We want to have a really big number. And so that's coming. But 1 million reads per second, that's pretty nice. In a 6-bench environment. We're working on some faster replication. As I mentioned, we are focusing on e-commerce primarily, and Magenta is one of our partners, so we're working on a lot of different enhancements to make specifically Magento and the e-commerce that uses that stack faster and better. In terms of the cloud,
When you're talking about transactions, we have reached per second. You don't involve any transactions, right?
well, we actually always use transactions, even reads. So it actually is operations, read operations, but you can use transactions.
But what this mean? I mean, if you have a transaction, basically, two items.
We use a sysbench, so the benchmark that we have used, let's see, it's a big big table. I think it's over 10 million records, and it's a part of the regular sysbench OLTP benchmark where you routing reads and writes. And in this case, we just use reads primarily, and that's we use a again, I don't know exactly the details of that, but we use a standard benchmark that we compare ourselves to others. So this is not a fabricated benchmark per se. So anyway, so we are working on the deployment and provisioning optimization, hooking into the templating environment that some of the vendors or platform providers have. And we also gonna do what we call instance testing or case testing, because as I mentioned before, when you get into a virtual environment, your networking, your CPUs, your memory, everything is virtualized. So at some point, you need to understand what are the performance characteristics of what you're getting. And so part of our, like flex up specifically would be to test the new node and make sure that it adheres to some performance envelope that we have specified. And then finally, our new admin architecture, which is will support a much improved web UI. We already have a web administration tool. But this new tool will also be a services-based, so it will allow you to basically interface your own tools like an IDEALS or something to this and monitor multiple clusters simultaneously. And a lot of the UI has a lot of simplified mechanisms in there. So here's an example of a dashboard. It gives you an instance view of what are the transactions, and then each individual, like serialization, the storage, the query latency is mapped out automatically. If you specify a threshold, so here, maybe someone said if I'm going over 70%, turn this red, means the health of the cluster now is red, and so it gives you the ability to get alerts when something like this happens. You can view this on the phone and take appropriate action. You can click on the various items in this case and then analyze it in more detail. Below that, there's a view of the transaction for the past 24 hours. So if you see any spikes, then you can dig into this even further. Another part of this is also ability to compare two data points in a cycle. So up here, we have the activity, and so you can zoom in to a data range, and then within that, you can pick 2 points and compare side by side what happened during that time. So what queries have been executed, what was the CPU load time. Right now, those are the 2 selected, but you can also look at a couple of other characteristics in the graph. So this will make it a lot easier to diagnose issues or be proactive and set thresholds where you want to have notification if like your transaction spikes up or your storage is running out of space, things like that. And finally, the flex up, flex down will be pretty simple. In this case, we have 8 nodes and we want to have 2. So those are already highlighted, and once you press the flex up, those will eventually join the rest of the nodes and form 11 nodes, so 10 nodes. So some final thoughts. So Clustrix, again, has gone through the design principles of the shared nothing and continuous improvement is to provide massive read and write scalability. We can support very high concurrency and linear scaling. So far, again, we have not run into any bottlenecks where we hit a wall. Elasticity, again, in e-commerce it matters because, and I'm sure in other types of workloads where you have to bring up a couple of nodes, bring up extra capacity, and when you don't need to flex them down. And just as simple as you would do with an application, you would do one of the ways. And this actually allows you to right-size resources to your price performance. And then finally, resilience, which is built automatically in there, so you don't have to do anything special. The data can be protected across multiple nodes, and we have customers go through very high throughput and concurrency in critical times where the databases work really well. We work in the cloud, so we work on AWS, we have an AMI, but we can also work on any environment that provides a centralized environment. So, and you can do on-premise, on the cloud, bare metal, and so forth. That's really it.
Robbie Mihalyi. We're going to take only one or two questions because we're a bit out of time, but Robbie will be here for one-on-one questions after your hand up, but both of you can win.
Okay.
One or two, so.
Well, first, thanks for the presentation. It's clear how you can survive a single point of failure. Now, what action, if any, would you take against a network partition?
Network partition. So network, when you lose network connection between multiple nodes, right? Well, you have, first of all, a split brain problem, right? So if there are equal number of nodes, then the cluster will win because it needs majority to form a core. So we usually recommend to use an odd number of nodes, right? Because at that point, if you lose it, you know where to. Right? If you have 5, there's going to be 2 and 3. So the 2 will know it's not to process anything, and the 3 will form the core of to process transactions.
Before we take the next question, I forgot to mention we are giving away ASYS ZenWatch in the next 3 minutes. Everyone has to have their card in that bowl that's floating around there. Yeah, please make sure it goes around and everyone has a chance. There's also swag in a bowl right next to you. Please pass that around to whoever wants it. Lots of swag remaining. And let's take the next question.
Thanks again for the presentation. My question is, does the resiliency setup remove the need for backup and restore? And if not, how does backup and restore work in this environment?
No, so we do backup. We recommend how to do backup and restore. And that is, again, it collects the data from all the nodes and doesn't take care of it. So it doesn't remove the need. We recommend backup.
Can you do point in time restore? Like that?
Yeah. Yeah.
Thank you.
While he's collecting cards, we'll take one more question. Don't forget, we do have selfie sticks. Everyone can take one on the way out. There's 2 boxes of them, so we have enough for everybody. Is that done yet?
Have you found the sort of sweet spot versus like number of nodes versus power of nodes? So if I can afford 20 middling boxes or 10, twice as fast boxes, which one is better? Or is there not really?
Yeah, we tend to prefer the sort of, how should I say, mid-range nodes, and more of them. So for example, if we had, let's say, 32 core nodes, and you do 2 of them, right? Well, I mean, you only can spread workload only to 2. You can take advantage of cores, multiple cores, but the fan-out for queries and transactions is not going to be as big as if you use 8 times 8 core nodes. That will scale much higher. So again, it's one of those things that depends on your workload. Multiple nodes with less power would work better.
We have no more time for questions, but Robbie will be here for one-on-one questions afterwards. Can I ask you to just make this up a second? While we're doing that, let's give a great big round of applause for Robbie Mihalyi. Look the other way, pull one out.
She wins. It's going to be it. I knew I should have bought a couple of cards.
This one. Okay, read it out.
Mark C. Hadfield.
Mark Hadfield, right there. Excellent.